Welcome everyone. In this lesson, we're going to be talking about tangent lines and velocity. And we're going to break this up into two parts. So the first part, we're going to see how to find the slope of a secant line, the slope of the tangent line, and the equation of our tangent line at a specific point P on our curve. In part two, we're going to see kind of similar calculations actually, just a very different application, but we're going to see how to calculate the average velocity on a time interval for an object that's moving in a straight line. And then we'll also be able to see how to calculate the instantaneous velocity for that object at a specific time. All right, so for part one, we're dealing with tangent lines. Let's start. And before we really get into it, just review some of the basics. Two important formulas here that we'll need to know. How do we find the slope connecting two points? So if we have a point P and a point Q, the way we calculate their slope is we look at the change in y and then we divide by the change in x. So we look at the y coordinate from point Q minus the y coordinate from point P, the x coordinate from point Q minus the x coordinate from point P. So this is really the change in y over the change in x. And it really doesn't matter if, let's get a better x there. There we go. And it doesn't really, the order doesn't matter here as long as you're consistent. So if you do the q coordinate first up here, you got to do the q coordinate first down here. You could do the p's first if you want to. All right, so there's our slope formula. Then for an equation of a line, the one we're going to be using most often is the point slope formula. And it says if you know the slope, m, and you know one point on the graph, here are the x coordinates and y coordinates for that point that you know, then we form the equation of the line using this formula. So y minus our y coordinate is equal to the slope times x minus our x coordinate. And when we look at this, the y here and the x here, these are the variables. Once we get this into, once we start plugging things in. So those are the variables. Slope m is a number, y coordinate should be a number, x coordinate should be a number. So the y and x here, those are the variables. Now if you look at this, these two things, when we're defining a line, there's kind of two scenarios. So as this formula is stated, in order to write down the equation of a line, we need to know a point and we need to know the slope. The difficulty comes if we don't know what the slope is, and as we're going to see. And in general, if you don't know the slope of your line, well, then you need to know 2 points. So just a quick note here. For a line, we need slope m and 1 point, or we need 2 points. Because if we have 2 points, then we can calculate the slope, and then we can use one of the points for our equation. So in order to find a line, you either need to know what the slope is, and then you also need 1 point, or you need 2 points. You need to know the two of the points that are on that line. Okay. So the question is, we want to construct, given a graph, we want to construct the tangent line at point P. And we're starting by talking about circles. So here we go. We got a circle here. Right here. Here's a, hopefully everyone sees that. We got a circle. And then we're interested in this point P. And we have some intuitive idea of what a tangent to a circle is. So there's some important characteristics. So here's our tangent line at point P. It's tangent, that line is tangent to the circle. And what are some of these important characteristics? Well, we know it should just barely touch the circle at that point. So we don't want it to, say, intersect the circle more than once. We want it to just touch the circle at that point. And kind of related to that is the tangent line, very close to that point. The tangent line should give us a very good approximation to our circle. So if we were to say zoom in on this point, you can kind of see what happens when we zoom in. Here we go. We're zooming in on point P. And right around that point, it's very difficult to tell where the circle is versus where the tangent line is. So you can see a little portion of our circle, and we can see our tangent line here. And very close to point P, it's hard to tell the difference. So, what we want, so at point P, the circle and the tangent line should, few things, they should look very similar, which that's what we're seeing. If we're looking right around point P, it's hard to tell the difference between where the circle is and the tangent line is. Yeah, once we move away from P, this circle veers off. But right in here, it's hard to tell the difference. They look very similar. And related to that is they have the same slope. So right at point P, the circle and the tangent line should have the same slope. They should be going in the same direction. So notice right at point P here, the circle and the tangent line are kind of going off in the same direction. So they have the same slope. And you can really think of slope, in this case, as kind of like a direction. It's telling you which direction to go in. So they're both kind of going that way in this case. So we have this intuitive idea for what a tangent line should be doing when we talk about circles. It should just barely touch the point of tangency. We don't want it to intersect more than once. And it should give us a good approximation of what the circle is doing at that point. And the slope should be the same right at that point. The slope of our tangent line and the slope of our circle should be the same right at that point. And so the question becomes then, how do we actually construct that tangent line? So the difficulty is, how do we figure out the slope? We only have one point. We don't have a second point. We don't want this tangent line to touch the curve twice. So we don't have 2 points to work with. We only have this 1 point. How do we actually figure out what the slope of our tangent line is then? And so the idea, and we can generalize this for just, functions, curves. So here's a curve, y equals f of x, graphed right here. And so the idea for how to actually construct the tangent line is kind of artificially create that second point. So what we're going to do, we're interested in the tangent line at point P. We're going to say, let's pick another point, we'll call it point Q, somewhere else on our curve. So we have these 2 points now. And so 2 points we can actually work with. So the difficulty with tangent lines in general is we either need to know 2 points or we need to know the slope in 1 point. So we either need 2 points or 1 point and the slope. So we don't know the slope of our tangent line. So you can kind of see here, we have what we think is going to be our tangent line to the curve. We only have, if we're interested in point P, we only have that 1 point. And we're trying to figure out this tangent line. We don't know what the slope is. And the tangent line, by its very nature, we only want it to just touch the curve. So right around our point of tangency, it should only touch the curve once. So we only have 1 point to work with. So that's the difficulty here, is in order to figure out the equation of a line, we actually need 2 points, or we need 1 point and the slope. And so our strategy is start with what we know. So let's pick a second point somewhere else on our curve, a little bit further away from P. We can draw in the secant line, we call the secant line, connecting those 2 points. So here's the secant line connecting points P and Q. Now obviously that's not the tangent line. But what we can do then is we can move this second point around. We can move this point Q around. And the idea is we're going to take this point, we're going to move it along the curve. We're going to let it get closer and closer to point P. And so as this point Q moves closer and closer, what's going to happen is this secant line is going to look more and more like what we want our tangent line to be. So we're going to let point Q move closer and closer to point P. And we've developed a way to kind of deal with this idea of moving something closer and closer, and that is with a limit. We're going to calculate the limit as point Q gets closer and closer to point P. All right. So let's see what we end up with. And we're going to end up with kind of 2 different formulas. We're going to start with this one though, because this one kind of comes from the construction. The second one is going to be easier for calculations, but this first one actually comes from the construction. All right, so let's look at our graph here. So we have our curve, which we'll say is y equal to f of x. And we have our point P, which we're specifying this point. So point P is kind of fixed. So in general, we say this happens at x equals a. So we give this a fixed number. So point P is happening, at some fixed number a. Okay, we're going to form our secant line then by choosing some other point Q, a little bit further away from P on the curve. And let's see what those coordinates for point Q are going to, or let's talk about the coordinates for point Q. So we know we're going to be moving point Q around. So it's going to be, the coordinates are going to be changing. So let's give the x coordinate a variable, and let's just call it x. So we know we're going to be moving point Q around. So it's going to vary. So let's make it a variable. So the x coordinate for P, it's going to be fixed. It's going to be a number. So we'll say a. And then for Q, it's moving around. So we'll make that a variable x. All right, so what are the coordinates then for these 2 points? So both of these points are on our curve. So the coordinates for point P are a, comma, f of a. So we just plug into our function to get the y coordinate. Same thing for Q. So we set our x coordinate, we're just leaving it as x, and then to find the y coordinate, we plug into our function, so f of x. All right. So what are we doing in this first slope formula? So we found our what is the actual slope of the secant line connecting those 2 points P and Q? Well, let's figure it out. So we have our slope formula. That was the first formula we looked at. One of our basic little line equations there. So it's the y coordinate of point Q minus the y coordinate of point P. And then we do the same thing for the x coordinates. Do the difference there, change in y over change in x. And let's fill in what we know about these 2 point values, the coordinates here. So the y coordinate of point Q is f of x. The y coordinate of point P is f of a. And then the x coordinate of point Q is just x. And then the x coordinate of point P is a. So we see right here, this fraction here, f of x minus f of a over x minus a, that's just the slope of the secant line. Now m here, m is the slope of the tangent line. So that's what this formula is giving us, excuse me, is the slope of the tangent line. So that's what we're actually calculating. All right. So what is this limit doing as x goes to a? Well, this is where the magic happens. So let's go back over to our graph. And what did we say? We're interested in the tangent line at point P. So we picked a second point Q that was close to P, but not quite there. So a little bit off, a little bit further away. And then we're going to move this point Q around. And what we want to do is we want to slide this point Q along the curve so that it gets closer and closer to point P. So if we do that, if we let point Q move along the curve so that it gets closer and closer to point P, what has to happen then is if we watch what happens to the x value has to get closer and closer to A. So as we move point Q along the curve closer and closer to point P, the actual x coordinate here has to get closer to A. So that's why we have this limit as x approaches A. What this is really doing for us is this is really giving us the behavior we want. Point Q approaches point A, or point P. All right. Now, this formula is good. So we have a formula now that actually gives us the slope of the tangent line. Slope of the tangent line is the limit as x goes to a of f of x minus f of a over x minus a. So this gives us the slope of the tangent line at x equals a. Let's throw that in there as well. Okay. Now, there is a different version, an alternative version. Both of these are perfectly fine, so I shouldn't say this one is necessarily better. But this is the one that we primarily used for actual calculations. And it just revises it, so it says the slope of the tangent line at x equals a is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. And there's a lot of similarities here, but there's enough that's different where let's talk about it a little bit. And the main difference here is this limit is using x's, this limit is using h's. So what does h represent here? Well, when we go back to our graph here, when we have our fixed point P, and then we're choosing this second point Q that's a little bit further off. But we want it relatively close to point P. So another way to kind of think of the x coordinate for that point, instead of just x, we could rewrite it as it's close to A, but we want it a little bit, more or less. So let's add a little bit extra in. So A plus H. So close to A, but we're adding a little bit in. So H, another way to think of H is it just tells us kind of gives us an indication of the distance between, not necessarily distance between these 2 points, but it kind of gives us how far off point Q is from point P. So we could rewrite this x coordinate as A plus H. Close to our P value, but just a little bit more or less, plus H. So if that's our x coordinate for point Q, well then the y coordinate would be f of A plus H. So we have kind of this alternative version for how to write point Q. And if we use that, so if we're letting x equal a plus h, well, what do we get here? Actually, you know what? Let's not even do that way. Let's do it this way. So if we have this alternative version of point Q, well, what's the y coordinate for that alternative version? It's f of a plus h. And then the y value is still the same, f of a. And then what's the x coordinate for this slightly different version? It's a plus h. And then we have minus a for our y coordinate for point P. And if we clean this up, the only thing that happens is in the denominator, a here minus a, the a's cancel. And we're left with just an h there in the denominator. And so we can see where this fraction comes from. Now, why is it the limit as h goes to 0? Well, if we look over here, if x is approaching a, well, then h is kind of telling us how far off we are, how far off the x coordinates are. So if x is getting closer to a, well, then that means h, which is really how far off we are, must be getting closer to 0. So h has to be going to 0. So just a little justification for why this is. As x approaches a, h must be approaching 0. So when we convert the limit, instead of x approaching a, the difference between those two x and a values must be getting closer and closer to 0. So this h value, we must be adding on smaller and smaller values. Okay, so we have these two slope formulas, and both of them are perfectly good to work with. We're probably going to work with this one a little bit more, but we'll try out both of them. Take both for a test run here. So let's start with example 1. We're given the parabola y equals x squared and point P with coordinates 1, 1. And let's just kind of go through some of the work here. Let's find the secant line for point P, connecting points P and Q, where Q is the point 2, 4. And what is the secant line, the slope of the secant line? Well, that's our y coordinate, the difference of our y coordinates divided by the difference of our x coordinates. So change in y over change in x. Well, let's plug in then our x and y coordinates all into this. So we know our y coordinate for Q is 4. And our y coordinate for P, you can look up here, there it is, it's 1. And then our x coordinate for Q is, 2. And then our x coordinate for P is 1. Oop, wrong one. There's our x coordinate. It's 1. So we get 3 over 1, 3. So the slope of that secant line connecting points P and Q is 3. All right, let's try it again. Secant line, let's get the slope of the secant line for connecting points P and R, where R is the point at x equals 1.1. Now the difference here, in the first one, we're given both coordinates for Q. For point R here, we're only given the x coordinate. So how do we find the y coordinate? And the way we do that is with just plugging into the function. So before we go anywhere here, we got to find the y coordinate for point R. And the way we do that is we plug in to y equals x squared, our function. Because that's what tells us. Tells us what the y coordinate is. So we just plug in. So what we're going to do is we're going to take our x coordinate, which is 1.1, and when we plug that in, we get y is equal to 1.1 squared, which is 1.21. So our y coordinate is 1.21. Now, we want to find the slope then. So now that we have both coordinates, then it just becomes using that same slope formula. So the y coordinates minus the x coordinates in the denominator. And if we do that, we have our difference of our y coordinates, which 1.21 minus 1. And then our difference of our x coordinates. So our x coordinate from point R is 1.1. And our x coordinate from point P is 1. And if we do the arithmetic here, we end up with 0.21 divided by 0.1. And when we divide by 0.1, really we're just moving the decimal place over 1 unit. So this is just 2.1. And there we go. We have our slope of the secant line for these 2 points. All right. Let's try one more of these. But this time we're going to find the slope of the tangent line directly at point P. How are we going to do this? Well, we're going to use our limit definition, and let's use the other one. Let's look at the limit as x approaches a. So f of x minus f of a all over x minus a. Perfectly fine to use this one. So here's our tangent, slope of the tangent formula, one of them. What is our a value? Well, our a value here, because we're talking about point P, the a value is just our x coordinate. So we can that's just telling us, the x coordinate tells us the a value for this particular point. So if a is equal to 1, let's fill that in. So we're going to have the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. And let's actually now fill in what our function is. So let's go through and evaluate our function. So what is our function? It was y equal to x squared. So for this first piece, I'm just going to end up with an x squared here. And then when I plug 1 into the x squared function, I get 1. Okay. And now this is just a regular limit problem that we've built up the machinery. So we know how to do these types of things. And as you'll see, whenever we do these slope of the tangent line calculations, these limits are indeterminate. So this is a 0 over 0 indeterminate form. And that's not coincidence. It's not like this is just a bad problem or anything like that. When we do these slope of the tangent line calculations, it's always going to be like this. So we always end up with these 0 over 0 forms. All right, so what can we do? Well, we've developed techniques on how to work with that. So we're going to, try to factor and cancel. So let's try to factor this numerator, and it factors very nicely. It factors into x minus 1, x plus 1, and then we have x minus 1 in the denominator there. And now that it's factored, we see that the x minus 1 pieces here show up on both the top and the bottom, so we can cancel them off. And as soon as we do our canceling, the canceling normally gets rid of the 0 over 0 form. So once we cancel, we're kind of ready to plug in. And so to evaluate this, we just plug in and we get 2. 1 plus 1 is 2. Now, why can we do this? Why can we do this step right here? Well, we're doing direct evaluation. And that's because our function, x plus 1, the function that we're doing the limit of right here, that's a polynomial. So we can just plug in to evaluate. So there we go. the slope of our tangent line is 2. We figured it out. All right, so it's a little bit of work to do these. That one's not too bad though. Let's try another one. Example 2, we're going to find the equation of the tangent line. We're given our function y equals 3 over x, and we're told, what point we're going to be looking at. Point P here is 3, 1. All right, but this time we're going to be finding the equation of the tangent line. So in general, how do we find the equation of a line? We need to use our point slope formula. So let's write down what that is. It says y minus our y coordinate is equal to m times x minus our x coordinate. And if we look at this, we need to know 3 things. So the y here and the x here, those are going to be variables, but we need to know these other pieces. So we need to know our x coordinate, we need to know our y coordinate, and we need to know the slope. What are these equal to? Well, the x coordinate is just the a value. So whatever, here we're given the x value. But it's wherever we're interested in for our tangent line. We're also given our y coordinate, but in case we weren't, how would we find the y coordinate? Well, we would take our x value, our a value, and just plug it into the function. So you just evaluate f of a. And then for the slope, how do we find the slope of our tangent line? So here's the slope of our tangent. How do we actually find the slope of the tangent line? Well, for right now, we have to calculate a limit. And let's use the other version. It's the limit as h goes to 0 of f of a plus h minus f of a all over h. And actually, this kind of a spoiler or a bit of a teaser here, we're going to call this limit, we'll give it a special name because this is going to show up quite a bit. And we're actually going to call it the derivative. So we kind of give it a special name here. We call f prime of a, the derivative of function f. That's really what we're calculating here. We'll get there. So right now, we don't know what this means yet. But just keep this in mind because we'll be finding equation of tangent lines. And this is just a good summary of how to actually find all the pieces that you need. X coordinate is the a value that's specified. Y coordinate, we just plug into our function. And then the slope of the tangent line, right now we're calculating this limit. But going forward, it's just the derivative where we plug a into it. Okay. So with that in mind, we know our x coordinate is 3. We know our y coordinate is 1. And we need to figure out m. We need to figure out the slope. So we're going to use this limit definition to do that. Let's try it out. And then we'll come back and finish up this tangent line business. So let's calculate our slope. So we know it's going to be the limit as h goes to 0 of f of 3 plus h minus f of 3, all divided by h. So I know the a value was 3. So I've taken this. I know the a value is 3, so I've just plugged 3 in. All right, so now let's actually plug into our function. So what was our function? Well, it's y equals 3 over x. So let's take this function here, or this value here, 3 plus h, and let's substitute that in wherever we see an x here. So I'm going to take this 3 plus h, throw it into this x. And when I do that, I'm going to get 1 over 3 plus h. And then same thing here. Let's take just 3, throw it into this function, and I get 3 over 3. So I get minus 1. Okay. And then all over h. All right. So we want to work with this limit. And it's not too bad. But we have some fractions up here. There's a big fraction here. So it makes it a little easier for us if we try to, pull these fractions apart. And what we're going to do is we're going to rewrite this as the limit, as h goes to 0, of 1 over h times 1 over 3 plus h minus 1. So not absolutely necessary to do this, but I find that it helps. And what we're doing is, instead of dividing by h, we're just multiplying by its reciprocal, 1 over h. All right. So now we got to work with this expression in the brackets here. And our kind of standard technique for that is to use the common denominator method. So we want to actually do the subtraction here. We want to get this into one fraction. And just to kind of go back, why are we doing this? Well, if we go to this point here, and I'm missing the 3. Arg. That should be a 3 up there. And this should be a 3 right here. If we were to plug in 0 in for h, I'd get 3 over 3, which is 1. So 1 minus 1 is 0. And then I get a 0 here. So we have that 0 over 0 in determinant form. So that's why we have to go through all this algebra. All right, so let's try to work with this terms in the bracket. Getting a common denominator, we're going to have the limit as h goes to 0. We'll have that 1 over h in front. And then we'll have our 3 over 3 plus h, and then plus, and I can just, or minus, minus. And then I can rewrite that 1 as just 3 plus h over 3 plus h. Really, I could think of it as, if I wanted to, I could think of that 1 as a fraction. Even though it's just a number, I could think of it as a fraction, so 1 over 1. And then how do we get a common denominator? Well, I multiply both the denominators together. So in order to make this fraction, match up with this, I'd have to multiply the bottom by 3 plus h, and then the top by 3 plus h. All right, so once we get this, we can actually do the subtraction then. We can actually combine those two fractions. So when we do that, I get the limit as h goes to 0. We have the 1 over h in front. And then we combine the numerators. So I get 3 minus 3 plus h all over 3 plus h. Do the subtraction. And just to be careful here, I'm going to distribute the negative to the 3 and the h. Easy to kind of miss that. The 3's cancel. That's nice. And then we're left with the limit as h goes to 0 of 1 over h and then negative h over 3 plus h. A lot of h's. Just seemed like I kept saying h. Probably have. All right, so now we're getting there. Things are simplifying down. But now we can cancel these h's. And as soon as we cancel this 1 over h, or that h in the denominator, that's kind of contributing to our 0 over 0 form. So normally as soon as we do that, we should kind of get ready to try evaluating the limit again. And when we do that, we have the limit as h goes to 0. And we have negative 1 over 3 plus h. And now we're ready. This is just a rational function in terms of h, so we can just evaluate. And we get negative 1 over 3 plus 0, negative 1/3. So again, the reasoning here is we can do direct evaluation because it's a rational function in terms of h. So, nice. So we have the slope. It's a rational function in terms of h. So this is the slope of our tangent line, negative 1/3. So that's kind of like the missing piece that we needed to find. So let's go back. We've done all the calculations here. Found the slope of our tangent line. Let's head back this way. We're just going to throw that in right here. We know the slope of our tangent line now is negative 1/3. So now we just take all these three pieces and we throw them into our formula. So we get our tangent line equation is y minus the y coordinate, so our y coordinate is 1, is equal to our slope, negative 1/3, times x minus our x coordinate. And that's perfectly fine. there's our tangent line. Now, a lot of times, though, we like to get it into the form y equals mx plus b. So we can just kind of simplify this down, distribute the negative 1/3, and then add 1 to both sides to get y by itself. And when we do that, we get y is equal to negative 1/3 x plus the negative 1/3 times negative 3 is plus 1. And then when we add 1 to both sides, it bumps it up to plus 2. So here's our tangent line. Yeah. Okay. There's our tangent line in y equals mx plus b form. So really either of these is fine. Normally we like to get it into this format though, but we start with our point slope formula to get us there. All right. So a little bit of practice doing these limits. In part 2, we're going to jump over to average velocity and instantaneous velocity, but a lot of the calculations are going to feel pretty similar. So we'll see you then. Bye-bye.